Welcome back to the latest video in our series on diffusion image filtering. Just a quick recap for what we did in the last video. We derived an explicit method for solving the one-dimensional heat equation, and this method had some issues. For instance, when you chose a too large time step, we saw that it was unstable, right? The high frequency modes would cause the solution to diverge. And in this video we're going to study implicit methods and which provide a way out of this problem. Okay, so first let us discuss the difference between the two. So here, when we have an implicit method, so I will draw what is called a stencil diagram. Okay, when we had an implicit method, we have here, this would be j minus 1, this is in the space coordinate, this is j, this here is j plus 1, this is L, and this is L plus 1. Okay, great. When we are in an explicit method, we use the Euler method to approximate the time derivative here, okay, and we approximate the second derivative by the central difference approximation here at time L. And the result of this is an equation where we can evaluate this guy as a function of these three. Okay. An implicit method is different, because in an implicit method, so let's see if I can get, so L and L plus 1 remain the same. Here we have j minus 1, this is j, here j plus 1. In an implicit method, we still approximate the time derivative of the Euler method, but now we approximate the space derivative at time L plus 1 in the future. It might look weird, but it works. And the idea is that once we gobble up all the equations like this, we end up with a matrix equation that we need to solve, and this value here at the time, it kind of becomes a source into this matrix equation, right? It is that independent vector that you need to multiply the inverse. And you see that this matrix is very, very easy to invert, and we can still calculate the time step L plus 1 in ON, and this method turns out to be unconditionally stable. Alright, so without further ado, let's go to the notes. And then here is what I said. So that we have the heat equation. This scheme, by the way, is sometimes called the backward time-centered space scheme. So we start with our heat equation, which is del U del T equals d del square U del x square. And if we do it like this in our new scheme, we now put the space derivative at L plus 1. We have UJL plus 1 minus UJL divided by delta T equals the UJ minus 1 L plus 1 minus 2 UJL plus 1 plus UJ plus 1 UL plus 1 divided by delta x square. And if we define alpha equals d delta T divided by delta x square, and we put all of the L plus 1 terms in the left hand side, we have minus alpha uj minus 1 L plus 1 plus u1 plus 2 alpha uj L plus 1 minus alpha uj plus 1 L plus 1 equals ujl. Alright, and this is actually a series of equations, right? It is valid from 1 to n minus 1. Actually, I said n, but it's actually n minus 1. Need to fix this later. And the idea is that we will write this as a matrix equation where the matrix A multiplied by a vector ul plus 1 equals ul. And this matrix, you see it's given by this. You have 1 plus 2 alpha minus alpha, where we already, here at the borders, we already put the boundary conditions that u0l equals 0 and unl equals 0, right? And then we have 1 plus 2 alpha, minus alpha, 1 plus 2 alpha, minus alpha, and this is a matrix like this, and then we need to solve these things, all right? And then in general, inverting a matrix equation is very, very expensive, right? But this matrix in particular is very simple. This matrix is what we call a tridiagonal matrix. See, there are only 3 diagonals which are not 0, okay? And actually the cost to solve this is only on, not on cube, which is the usual complexity for solving a matrix system. And you can see why if you think in terms of Gaussian elimination. So suppose if you were to apply Gaussian elimination to this matrix, you would start this term, right? Here, oh, I cannot highlight it, that's okay. Would start at this first term, and then you would multiply it by a factor and then add this row to the next one to make this guy go to 0. And that's it, right? And then while in traditional Gaussian elimination, you would like take n multiplications to add a row, and then you would need to repeat that n times, and then this when the procedure of zeroing out a column in traditional Gaussian elimination would be on square. For this matrix, just O1, because you only need to perform like 4 multiplications or something, and then you would do this until you go to the end, zeroing out this previous diagonal, and then when you reach here, you would do back substitution, and this back substitution is also O1, right? This is like one way to do it. It is not the preferred way, because the way I described is numerically unstable. We'll later see why, but it is just a way for you to see that inverting this matrix is pretty easy, right? And then this is what's called an implicit method, because instead of before where we have an explicit algebraic relation to find this guy, we actually have an equation that gives us the answer, and then we have to solve this equation. All right? And now, if we perform the stability analysis, same stability analysis that we performed for the for FTCS scheme, but in the BTCS scheme, it's like the same thing. We would substitute the ansatz there, AKI e to the power of ij k delta x. But here, if we do that, the only difference is that there's this ak here, right? Before there wasn't this ak, and that changes the story completely, because if we isolate, we now have 1 divided by 1 plus 2 alpha 1 minus cosine k delta x. Then if we do the analysis, the 0 mode k equals 0 still has ak equals 1, because cosine of 0 is 1, 1 minus 1, 0, so 1 divided by 1, which is 1. But again, the 0 mode needs to have an ak of 1. They do not decay under the heat equation. But now the most dangerous Nyquist mode, which is k delta x equals pi, cosine of pi is minus 1, so this will be 1 divided 1 plus 4 alpha, right? And the amazing thing is that we have ak is between 0 and 1 for every alpha that we choose. So we can take any time step that we want, and the method is unconditionally stable, right? Very powerful result here. Very useful. So now if we go to our code, so first I will plot this just show what I'm doing. I am here plotting the frequency response, same thing that I did for the explicit one. There's the exact one, which is like this exponential, and the BTCS frequency here, right? And then now I'm plotting for a very, very small time step, which is t equals, well, it is not really all that small. It is still larger than the time step. If you remember, the largest time step which we could use for the explicit method for this system was the half of this. It was 0.00005. This is double it. And then if we plot this relation, look at this. So you see that the exact one is an exponential decays like a Gaussian, right? And the BTCS one also decays, but decays lower. So you see that we have like an overestimation of the larger frequencies, but the important thing is it's always between 0 and 1. So you can imagine that when we take the nth power of this curve, we take several time steps, it will become closer and closer and closer to the exact one. And the nice thing is that we can just take like much larger time steps, like for example 10 times that time step, it will still be between 0 and 1. The overestimation now is much larger, but you can see it is still it is still stable. And same thing if we go, for example, very, very small ones, you see the same pattern. It is not like the first frequency response of the explicit method where sometimes it would, for very small, if you remember the FTCS method, for very small time steps it would be above the exact curve, but for very large ones it would be below. But the BTCS method, the implicit method, it is always above. It doesn't matter which time step that you take, right? With this in mind, we can go to our code. So the BTCS system, so just to show here what I'm doing. Again, I am taking this signal that we are all familiar with from the previous videos. I'm sampling this signal. I am solving it with the FFT for the exact solution. And then when I come here, you see I am now picking an interval of 10. If you remember, the minimum value of m for the Euler method that we could pick was 40, or else it would be unstable, right? And then what I'm doing here, okay, I set up the main diagonal, which is 1 plus 2 alpha times an array of n minus 1 ones. So if we go here, okay, so it is this main diagonal here, right? And the lateral diagonal, which is minus alpha times 1s. Well, it actually has one less size of this, but this is a SciPy convention. For some reason, SciPy will not accept if I put n minus 2 here, which is the correct one. You see, it's actually n minus 2, but NumPy doesn't like if I put n minus 2. And then this is just to tell SciPy that our diagonal is minus 1, 0, and 1. So this is the diagonal below, this is the main diagonal, and this is the diagonal after the main diagonal. And one thing to remember is that since this is a sparse matrix, make sure in the numerical library that you're doing, you use sparse matrix convention. You don't use like normal ones, because or else it would waste space saving all of these zeros, right? And then we call, where is it? Here. We call m times, say that y equals linear algebra solve the matrix that we built y. So what this does is it solves the matrix, the system have matrix times x equals y, and then it gives x, right? It is like very, very important. So it's when you use like any numerical package, really, don't just invert the matrix and just say, okay, I want in this case matrix minus 1 times y, because sometimes inverting the matrix can be a more expensive operation than like solving the linear system. And when you actually ask the library to invert the matrix, it doesn't really know that you want to just solve the linear system, so it performs the more expensive operation. And if you call the solve method only, you're good, right? So it can already look for optimizations and, well, run your code faster. All right, so if we run this like it is, so it is solve BTCS. Let's see what we get. And you see, it is the FFT is yellow, BTCS is green, and it fits perfectly with only 10 time steps, right? And the most amazing thing is that it's stable for like any time. So suppose I just put like 1 time step, for example. You see that it is not exact. It is a very reasonable approximation, but you can see some difference here. But it is stable. It not diverge like the forward time-centered space method. And we can see more or less where the error is. It is because you see those oscillations here. It is oscillating with respect to the main signal. And then this is simply because, as we saw, the frequency response of the BTCS method, it overestimates the higher frequencies with respect to the exact one, right? So sometimes this is not a problem. Sometimes you could get away with a solution like this. You just should understand the power of this method, because only 1 time step, it was already enough. So very, very interesting stuff. And if you want, you could like search which value of m is the smallest value of m you can get away with, and then see m equals 4 is already, you can see some very, very small difference, but you see this method is pretty good. All right, cool, that's it. And then, so just like as a last way to visualize, so where is the magic here? Because if you remember from our theoretical argument, we could understand the instability of this method here, because this should only be valid when we have a kernel that is a Gaussian of this width, right? And when this approximation is no longer true, we would have an instability of this method. So why is this one here working even with larger time steps? And the idea, well, now I am going to do what I told you not to do. I would just invert the matrix, but it's just for us to visualize, because it becomes really clear that, so I'm gonna do a spelinaug inv matrix, and I will pick the 5th line, for example. And then if I run this, let's take a look. You see, so this is the middle line of the vector. You see that we have values for every column, and then it is more centered at the middle. You see, we have here, this guy is 1.4, 10 to the minus 1, then we go to 2.18 to the minus 1, and then it becomes a, right? So what's happening is that when you solve this equation, even though you have a tridiagonal equation, very, very small, so can be solved very fast, when you invert this thing, what you actually get is a sort of a Gaussian with a very, very large width. Okay, it is what is more or less represented in this line. So because when you invert this method, you can get this very spread out Gaussian, even though you're not writing it explicitly. This method is valid for much larger time steps than the explicit one, and that is more or less why it works. Alright, so that's it. We are almost done. As you can see, we had much less theory in this video than in the previous ones. And this is a tendency as the course goes further. We'll have less and less theory and more practice, which for me is a good thing. Don't know about most people. But anyway, we with this video we have managed to fix the problem of the instability of the numerical method to solve the heat equation, but we still can do better, which is what we'll see in the next one. We'll see that the Crank-Nicholson method, which is kind of an average between these two, gives a more accurate answer for most cases, and then this is what we're going to study. So until there, I'll see you later, and bye bye.